let's quickly look at this quick question on calorimetry. The question reads 0.5 kg of water at 10 degrees Celsius is completely converted to ice at 0 degrees Celsius by extracting 188,000 joule of heat from heat. Now, if the specific heat capacity of water is for 4,200 joule per kilogram per degree Celsius, calculate the specific latent heat of fusion of ice. So in this question, we are asked to find specific latent heat of fusion. And the symbol for that is capital L subscript F. And that is what we are asked to find. And specifically for that of what? Ice. So take note of that. Now basically, let's write out all that was given in this question. Solution. Let's write all that was given in this very question. We're told that the mass of water was 0.5 kg. What else did they give us? They said it was initially at a temperature. We call that theta 1 at a temperature of what? 10 degrees Celsius. Okay? Then it is then converted to ice at 0 degrees Celsius. So the theta 2 is 0 degrees Celsius. Okay? Now what else did they say? By extracting 188,000 joule of heat. So we're giving the value for capital H, heat, in this very question. They say that is what? 188,000 joule. Now that is what we're told from it. Then I said if the specific heat capacity. Now mind you, specific heat capacity is different from specific latent heat. Okay? And the symbol for specific heat capacity is small c. And they said for that of water, it is what? 4,200. It has a symbol. For specific heat capacity, the symbol is joule per kilogram per degree Celsius. Or you say degree or per Kelvin. What am I saying? Either you say joule per kilogram per degree Celsius, or you say joule per kilogram per Kelvin. So take note. So this was given for that of water. For that of water was given. And the question says we should find the specific latent heat. Latent heat of what? Fusion. That I wrote subscript F. For that of ice, we have to find it. So in this question, it's unknown. Now, we are going to be analyzing this question carefully. Carefully. Now, we know in this very question, if you go by it again, we are kind of talking about a change in state, is it not? And a change in temperature too. Observe something. The water was initially at 10 degrees Celsius. They said that it's converted to ice at 0 degrees Celsius. Now, there are a lot of changes that have occurred from water at 10 degrees Celsius to ice at 0 degrees Celsius. Let's analyze carefully. Now, if water was cooled down, or let's say heat was removed from it, it will therefore take the water from a temperature of 10 degrees Celsius to water at 0 degrees Celsius. So what am I saying here? I am saying water at in bracket 10 degrees Celsius will therefore be converted to water at 0 degrees Celsius. Okay? So you have to know the amount of heat that was removed, because when heat is removed, the temperature will decrease. So how much heat was removed from water at 10 degrees Celsius so that it's not so cold that it becomes water at 0 degrees Celsius? The formula we will use to get that is mc theta. Okay? Let me expand it better. mc change in theta. So these are the three things to be times it together that will give us the amount of heat removed such that water at 10 degrees Celsius become water at 0 degrees Celsius. Now what other change will there occur? This water at 0 degrees Celsius will then undergo what they call a change in state. No longer a change in temperature. Now because it will undergo a change in state, we now say water at 0 degrees Celsius will now become solid water, which we call what? Ice at that same 0 degrees Celsius. And mind you, because this is involving a change in state, not like this one whereby only temperature was changing. In this case, temperature is never changing. Observe it. What actually changes what? State. from liquid water to what? Solid water, ice. So the formula we will use to get the heat removed to cause this change in state will be a different formula. And in this case, we are going to be using M times L subscript F. And this L subscript F is what you are going to be looking for. Now, they told us that the total heat that was removed is what? We already have the value for it. They said is 188,000. So it means that 188,000 is gotten by adding the heat you will get from MC theta theta to ML subscript F. The total heat added will be equals to this. So I can now draw my equation from that. I will now say 188,000 is equals to, what is the first heat? The first heat is MC change in theta. Then what is the second heat? The second heat is M times L subscript F. So guys, we can now simply impute all these formulas, all these variables into this, and then we will solve and get our answer. We've already imputed our H to be this. So let's get our M, our C, and our change in temperature. Okay, let's do that right away. We'll now say 188,000 is equals to, now I'll be making use of my calculator to make everything faster. And to save space. What is our mass? Our mass is 0.5. So I will type 0.5 times, what is our C? Our specific heat capacity. For water, it is what? 4200 times what is our change in temperature. Now mind you, the initial temperature was this and the final temperature was this. Now since this is a cooling process from a higher temperature to a lower temperature, what is actually the change in temperature? Final temperature minus initial temperature is what? -10. Now the minus there is only telling us that it is a cooling process, not a heating process. If it was +10, that is a heating process. But since it's -10, it shows and it corresponds to the fact that it is a cooling process. Mind you, you will not take note of the minus when solving. So don't use anything like -10 here. It's simply 10. So I will now say times 10. I hope that is clear. Now the final value for this gives me 21,000. Okay, 21,000. Then plus, what is our M? Our M is 0.5. 0.5 times L, it will be 0.5 L. Like I said, subscript F. So what do we simply do? Move the ones without LF to one side. So we say 188,000 minus what? 21,000. Let me quickly write that out. Okay. Alright, let me quickly write that out. It will now be this minus 21,000 equals what? What is here? What will be left? 0.5 L subscript F. So let's do the minus together. 188,000 minus that gives us 167. 167. So write 167,000. That's what we got. Equals 0.5 LF. So because we are looking for LF, not 0.5 LF, we are going to be dividing both sides by what is attached to what? LF. And what is that? It is 0.5. So over 0.5 over 0.5. So what will happen? 0.5 will cancel 0.5. L subscript F for i's will now be equals to, what do we have here? We bring it that way. We have 167,000 over 0.5. So basically that is what we now have. So let's do that division. Our LF will now be equals to, let's see what that will be. 167,000 divided by 0.5. It gives us exactly 334,000. Okay, 334,100,000. Okay, 334,000. Now, what is the unit for specific latent heat? Whenever you have to find specific latent heat, whether it is of fusion or of vaporization, the unit to add to it is, watch out, joule per kg. It is not going to be joule per kg per degree Celsius or Kelvin. You are going to just stop here, okay? But if they say specific heat capacity, you're going to be adding per degree Celsius, or you say per Kelvin. So therefore, 334,000 joule per kilogram is the value for our specific latent heat of fusion of ice. I hope this method of solving was clearly understood by us. Thanks for watching.